So today's lecture is on transaction ordering algorithms and MEV. So basically, what ordering algorithms is used in sequencers, where sequencer node like orders the transaction to get the maximum economic benefit. And there are many algorithms that we can use for ordering the transactions. And we will be discussing here some of the most known or most used algorithm that are currently being used in this area. So, first of all, yeah, we will be starting with transaction ordering, and the first one is first come first serve algorithm. So, as the name suggests, the first tran it is like ordering a transaction in the way where when uh, suppose transaction tran- transaction A, sorry, in suppose transaction A came, and uh, in that way, let's say after came transaction B, C, and D. So in the block, when the sequencer is mining the node, uh, it it will be the first transaction that will be included will be transaction A, then transaction B, and C and D. So there is no like the first of all the selection of the algorithms is based on the priority order of uh, a high fees, high gas price that the like transaction that the person who's like submitted the transaction is paying, and after the transaction are selected, uh, they are ordered in this first come first serve algorithm, and this just is like the main aim here is to like tag the transactions as much as they can, and also like do it in a most efficient way possible. The so second transaction second ordering mechanism that we'll be learning is like permitted graphical arrangement. So here the transactions are treated in a way where like yeah, first of all, like the transaction are treated like a mm, graph structure. So there are like some kind of relationships in the transactions. For example, some transaction may be the parent transaction of some other transaction that is included right now in the mempool, and and so this in this way we are like establishing a graph-like relation in between them, and when then we order them in a like some fashion. Most popularly known is nested dissection, where they are dissected or like arranged in a recursive fashion. Like there are three algorithms that are particularly used in like executed PGAs. So first is Kutil-Mackey algorithm, second is nested dissection, and third is reverse Kutil-Mackey. So I'll be talking about nested dissection here. Uh, uh, can you see this screen? Like I'll share the wait, I'll share the entire screen. Like can you see this desktop, like the whiteboard?
Yes.
Okay, so in PGA, like suppose the transactions are in this manner. You say A, B, C, and there are like suppose n transactions in this way. What what happens is uh, now I have first selected n transactions on the basis of the priority gas fee that the person is paying me. And now what I will do is, after I've selected these n transactions, I'll like order them in recursively for for most bandwidth efficiency. And like I just break it into two parts, n by two and n by two transactions. So this is kind of like a divide and conquer algorithm that is like will be most known with. So now this bigger problem of ordering these end transactions is now broken down into uh, like solving two sub problems with length n by 2 and n by 2. And now recursively this will be called here same function. And after that, this again will be broken into pieces of n by 4, n by 4, and n by 4, both of these as well. So this goes on as n by 2, whatever becomes k1. And on this is the like base level where the transaction is sorted in itself, and then it like goes back again and recursively computes the answer. And so this is how it works. First, n transactions are there. They are broken down into n by 2 and n by 2. Now this goes on. This is kind of like a binary tree. And after the execution is completed at the leave nodes, they come back, and then we get a ordered transaction list here as the answer. This is how like nested dissection is working. Yeah. Or yeah, this is about PGAs. And then comes transaction narwhal and bullshot. So this is a recent transaction algorithm with the new like BFT analysis concept, BFT consensus that is like introduced in a recent paper in 2022. I think Aptos is the one that came up with this, and it is currently being used in Starknet. So here we are like considering the mempool as a like directed cyclic graph based structure, a DAG based structure. And the transaction ordering here is kind of complicated, so I like break it down it in more easier fashion. So what happens is now that there is a new BFT consensus mechanism here. So what happens is like consider these as nodes, these nodes as validators, and this is one particular round. So this is rth round, r plus 1th round, r plus 2th round, r plus 3, and so on. So what happens here is they are connected in any manner. This is a like DAG, so there won't be cycles in it. So like I'll be connecting this one and now this one only for demonstration purposes. Yeah, so right now we have four of these nodes or validators that we have. So there is an execution that happens in like odd round and even rounds. So the transaction ordering happens based on an anchor. The anchor is the leader node that is selected uh, just in like the leader node is selected in the even rounds. And from the even rounds when the leader nodes are selected. In the odd round, their transaction inclusion or transaction ordering happens in this round. So I'll just say like this is my leader node for this. Let's say r plus 1 is like even, and here I'm picking this as my leader node. This is known as an anchor node where I'll be anchoring my transactions off. So what happens in BFT is you need to have, suppose there are F Byzantine generals. So you need to have F plus 1 support to like execute something in a P2P or P2P network or a decentralized network. So this is common knowledge in blockchain. So now we know there we need two nodes here to select validate that we will be interacting or will be included in this node. So this is the odd round, and here I'll be like uh, connecting these nodes with itself. Mm, okay, so I can see that there is one node that is connected with the leader here. This node is counted as a vote. So in the odd round, these nodes will vote for the like this leader node if they have a connection with them. So since this node has a connection with this node, it will vote for it. But since this is not enough because we need two votes, we will not include any transactions in it whatsoever for now. So a new leader will be selected here. Suppose this is the new leader, and I'll assume that this got support from the next two nodes and it got two votes. What will happen is now this will look, first of all, if there is uh, this condition which happened here that it did not get full node, like full support of F plus 1 participant, nothing will execute and it will like uh, execute it in the next odd round if the condition meets. So now that the condition has met, it will look for like a path so that this leader node, leader 2, is connected with leader 1 in some manner. So this path like right here, and I'll suppose that it is also connected with this path right here. This is the path that we can connect with this leader node and L1 node. So what will happen is this leader node was, let's say, is connected with this node. So all the transactions that happened here, all the batch of transactions that happened in the like interaction between these nodes will be included in the block that will be mined by L1 or by L2 in this odd round. And after, like, suppose R plus 4 and R plus fifth round, when there is another L3 and this is connected with L2, all these transactions that are here, like all these will be included because I can trace back these nodes uh, with this node here. And I'm supposing here that this is the only connection that I have for this L2 node here. And after this execution, all these transactions, all these batches here, batches of transactions will be included in the block, and this will go on and on and on for forever. And this is how like the transactions will be selected for ordering, and after that it is just high fees and high gas prices that uh, will be like the factor where we will see that which of these nodes that which of these transactions that we have in the mempool will be included in the block. So this is all for Narwhal and BlocSoc. Now we'll go into MEVs. Yeah, so initially it was known as minor extractable value because only the miners were able to extract this. Uh, but now since we have POS, like the host stake network, uh, it is now known as maximal extractable value, which means that the maximum amount of profit, the maximum amount of financial profit that the block producer can get by manipulating or ordering and arrangement of transactions in a block. So we can, the validator can include or exclude any amount of transactions from the mempool, and like he or she or the validator can choose where he's getting the most profit from. So now this is MEV, and these generally are the transactions that have high fees because these will be the one transaction. These will be the transactions where the validator will be getting the most benefit from. So there are also other participants in the network, searchers. So what searchers do is they are like always looking into the mempool, and they have their bots and algorithm to detect these high juicy transactions for high MEV opportunities, and like they extract like they have an extraction process automated for this, and these that is why they are known for they are known as searches because they are always searching for these transactions in the mempool. And once a searcher like has seen a transaction where there is high MEV opportunity, but that MEV bot will do is included include a similar transaction with higher fees, and then since the fees are higher, there is a higher chance that that the MEV bots transaction will be included, and that original transaction will be excluded from the block. So this is how they play, and there are a lot of MEV bots. So what happens is, uh, suppose the bot is getting $100 of benefit from the MEV opportunity, the bot will like give off approximately 90% of its profit to the validator because uh, of other the competition from other bots. If like it goes for a 10% benefit to validator and 90% to itself, other bot will come with a 20 to 80 ratio. This like percentage is included in the fees itself, or like the gas price that we have. Uh, so this is how like they distribute their uh, they distribute the profit. Uh, every time anyways the validator will be getting 100% of its profit because it doesn't mind. Just that the MEV will try to like uh, gain of the financial benefit that the uh, bot can gain from this that transaction. So there are many examples that that these MEV bots do. They do what they do is DEX arbitrage. So in DEX arbitrage, what happens is, suppose there is a transaction in Uniswap, and there is uh, suppose a person willing to give one ETH for let's say 100 mm, USDC. What will happen is the bot will come and front run a transaction, let's say transaction X, and also will give a transaction that will be included after this transaction, transaction Y, let's say. This will be with higher fees, higher gas price, and this will be with lower gas price. And what will the bot do is change this ratio. So there is always a slippage tolerance in like the swaps that happen. So it will the bots will try to uh, push off the like transaction to the maximum slippage that can go and like take all the uh, this difference in price that is created, and then they like uh, take the advantage of this and make profit with it. Also, there is liquidation. So some let's say that some person's position got liquidated. So their assets are now up for sale for like really low prices. The bots will come up and will give like high gas prices to buy up these assets that are like there for very low prices, and this like helps in very fast liquidation by these MEV bots. Uh, Also, there are sandwich attacks. Like this is also kind of a sandwich attack that I explained. This Dex arbitrage attack, and also there is front running. So if there is a transaction that is happening, like that is like not happening, like that is included in the mempool, and the this bot sees a opportunity of like exploiting this transaction. The bot will do is create a similar clone of this transaction with a higher gas price, and since this is higher gas price and they are similar, this will be executed and this will be not. So this is how front running happens. Yeah, the good and bad. So MEV is both good and bad in itself. So good is like this DEX arbitrage ensures that they get correct prices for their token. So like in this way, like this happens like constantly, and even the MEV bots are being MEV sometimes. So this problems is kind of mitigated always, because if there is some MEV bot that is trying to push the slippage tolerance to the right, there there will always be a another bot that will like push it to the opposite end, and this kind of maintains the price at the middle. This is like some kind of and basics of how this goes. And this landing protocol, as I explained, liquidations happen very fast. So if there is a uh, position which has gone below the liquidation ratio, this will be liquidated very fast, and will not that position will not be there for too long, and will not be like in a worse situation further. The bad of MEV is like this sandwich attacks. Uh, at the time of sandwiching, even if the other users are getting a fair price, the person who got sandwiched will get a like increased slippage, and like you will be in a net negative position with this trade. And this is kind of bad. And this generalized gas uh, gas price, like these containers that like are in that scenario generally increase the gas price uh, of the to execute the transactions, because there is always a risk of like getting front run by an MAB bot. So this like is a net negative for the Ethereum ecosystem, and like they, because of MEV bots, there will always be uh, like scenario will have to pay higher gas prices. And one instance with this is that when the MEV boost was introduced, there was like 50% reduction in gas prices. MEV boost and MEV auctions when were introduced, 50% of the gas prices were like reduced at the time. The solution for this is like using flashbots and maybe boost. And there is a proposal builder architecture in there in Ethereum. You can like search for it. These are the current solution that we have for like for the MEVs. And yeah, these are the references for it. And this is all about the presentation. If anybody has any questions.